In earlier parts of this series on spectrum analyzers, we talked about the basics in part 1 and then carrier measurements in part 2 and modulation in part 3 with some other topics thrown in. I thought it might be a good idea, however, because when I did the phase noise measurements in the earlier part, there were a couple of things that I didn't mention that might be important. If you're doing phase noise measurements in a laboratory environment, in other words, where the measurements really are important and you want to get them as accurate as possible, you do have to realize first that phase noise is just the FM noise. Also, what you're attempting to measure is a power ratio between the carrier and the noise. You can measure power several different ways. The definition of phase noise is in terms of RMS, or root mean square power. However, a lot of spectrum analyzers have a peak detector. So in that case, you're measuring peak power, not RMS power. Also, some spectrum analyzers have an average power. Once again, that's not RMS power. You want to make sure that you either are using RMS power or that you convert the phase noise or the carrier to noise ratio into an RMS figure if you're going to use it for accuracy. Another thing that I may have glossed over is the delta frequency, that is how far from the carrier that you measure phase noise. And here is an example. What I'm talking about here is the distance from the carrier frequency to the point at which you are measuring the noise. You're not actually measuring all of this noise. You're only measuring noise in an area around this point based on the resolution bandwidth. So I only point that out because the delta frequency is important. And as I pointed out when I was talking about the phase noise measurement, you always want to make an adjustment for the resolution bandwidth because phase noise is always specified per hertz. That is, the bandwidth is assumed to be a 1 hertz bandwidth. And therefore what you do is you use an appropriate resolution bandwidth, and then you adjust using the formula that I showed you, where to basically divide by a number in logarithms or in decibels, you simply subtract. So if you haven't watched parts 1, 2, and 3, you probably should go back and watch those, not only because they will help you understand what I've just been talking about, but also because to do the additional measurements that we're going to do in this part, which are adjacent channel power ratio and occupied bandwidth, it is important that you have a fairly good understanding of the basics as well as a fairly good understanding of how spectrum analyzers work and how you set them up to do various measurements. So what we're now going to do is we're going to do an adjacent channel power ratio measurement. Once again, we're going to use the trainer that you can purchase from Instek. And once again, the experiment is detailed in some depth with this RF and communication trainer manual, which you can download from the Instek website. So here is what we're going to do. We're going to set up a main channel at 880 megahertz with a main channel bandwidth of 2 megahertz, a main channel space of 5 megahertz. You'll see this in a minute when we set up the spectrum analyzer. A first adjacent channel with an offset of 2 megahertz and a bandwidth of 0.8 megahertz. A second adjacent channel which is 4 megahertz offset and with a bandwidth of 0.5 megahertz. Now, to understand what we're trying to accomplish here, the whole idea of measuring the adjacent channel power ratio is to see how much of the power, in this case, the power within this rectangle, is what you really want to transmit. In other words, you want all your power to go into your channel and none elsewhere. Now, let's look at what we are actually doing here. This is the frequency of interest, the center frequency or the carrier frequency. This is an adjacent channel. And take, for example, a cell phone system. You would like to put all your power in your channel and none in the adjacent channel, but of course some will leak out, and you're interested in the ratio. How much is leaking out? So this is the power in your channel. This is the power in the adjacent channel, and there is usually a lower adjacent channel, an upper adjacent channel, and then a lower second channel, an upper second adjacent channel, and so on. But the ratio is the ratio of your maximum power, that is your carrier power, to the adjacent channel power, which is this value. So let's set up to do that, and we will attempt to measure this adjacent channel power ratio using the Instek spectrum analyzer. I have set up the trainer to generate an 880 megahertz FM signal with a 2 megahertz total bandwidth, in other words, a 1 megahertz deviation. The span of the spectrum analyzer is set to 10 megahertz, and the reference level is set to 0 dBm. I think I'm going to change that to minus 10 dBm. Now we're set to do an ACPR measurement. To set up a measurement, we press the measure key, and you then do a channel setup. In our case, the main channel space is going to be set to 5 megahertz, the main channel bandwidth to 2 megahertz. You may notice now it gives you a variety or a menu of things to set up. The first adjacent channel has a bandwidth of 0.8 megahertz and an offset of 2 megahertz. So adjacent channel 1 bandwidth, 0.8 megahertz. The adjacent channel offset is 2 megahertz. The adjacent channel bandwidth for channel 2 is 0.5 megahertz, and the adjacent channel 2 offset is 4 megahertz. And now we will return. Now we have turned on adjacent channel power ratio, and you'll notice that the scope, the analyzer splits into two screens. The top screen is the 1 megahertz FM, 1 megahertz deviation FM signal at 880 megahertz, just as before. And then below it are the ACPR measurements. And you may notice that it says the channel bandwidth is 2 megahertz. The channel space is 5 megahertz, as we said. The channel power is at this time set to minus 0 dBm. Remember, our reference is minus 10. The adjacent channel bandwidth 1, 0.8, offset of 2. Bandwidth 2, 0.5, offset of 4. Then it gives you two measurements, and I'll zoom in a little closer so you can see those better. The first is the lower adjacent channel power ratio, and of course there is one for the first channel and one for the second channel. The first channel reads about minus 40. The second channel reads about minus 52 or 53. The upper adjacent channel for channel 1 and channel 2 read approximately the same. This one is saying it's about 28.6 or 29 as compared to 40 for the lower channel, and the upper adjacent channel 2 is 56 or 57 dB. What it is saying is the lower adjacent channel 1 is about 40 dB down, and then the second adjacent channel is about 52 or 3. The upper adjacent channel isn't quite as good. It's a little bit, it's not quite as far off our carrier power, so we're putting a little more power into the upper adjacent channel, both the first adjacent and the second adjacent channel. Let's now set up to measure the occupied bandwidth of this same signal. Let's take a look at what it is we're actually trying to measure with occupied bandwidth. There are two accepted measures for occupied bandwidth. One is called the XDB method, and that's how far down the signal is in decibels. So you pick a certain amount of a certain distance or a certain power ratio. Give you an example. Here is an XDB measurement that is done. This was done on an Anritsu spectrum analyzer, and you'll notice that the occupied bandwidth is specified in terms of XDB. In this case, 30 dB is the ratio that we're looking at. There is a second method that can be used, which is the percent method. That is the method that we are going to use. In this case, they are using 99% of the carrier. We instead are going to use 90%. We could set it to 99, but for purposes of staying with the experiment in the Instek manual, we will stick to 90%. So let's set that up on the Instek and measure the occupied bandwidth. The first thing we do is we turn the adjacent channel power ratio measurement off and the occupied bandwidth measurement on. Then we do channel setup. The main channel bandwidth remains the same, that is 2 megahertz, but we are going to change the main channel space to 10 megahertz. And you see here we have the OCBW measurement with a channel bandwidth of 2 and a space of 10. The OCBW percentage is 90%. That's what it's attempting to determine, or that is that's the parameter we're using. And it says the channel power is about 0 dBm and the occupied channel bandwidth is about 1.92 megahertz. Well, what I've done, I can't get it to set exactly at 2 megahertz. It's a very coarse adjustment. But what I have done is I just set it to a lower value. And you will notice now that it says that our occupied bandwidth is 0.88 megahertz. And you may notice from the shape of the waveform that we have lowered our occupied bandwidth quite a bit. And what I've done is just lowered the level of the FM deviation so that the VCO is only deviating about a megahertz total. That is a half a megahertz each side of the center. So that is the way that you measure occupied bandwidth. Of course, the reason you want to make these measurements, you would like to have all of your channel power in your bandwidth, that is in your channel, not in the adjacent channels, not only because it might interfere with another, for example, let's suppose this is a cell phone tower. If you're outside your channel, but that adjacent channel also belongs to you, that is to your company, you're interfering with another of your customers. If, on the other hand, that adjacent channel belongs to another company, you're interfering with your competitor. If you interfere with your customer, you may lose some customers. If you interfere with your competitor, you may wind up having to answer to the FCC. So those are things that cause people to take measurements of things like occupied bandwidth and adjacent channel power ratio very seriously. And it's one of the reasons why that this Instek, for example, which was developed to do measurements in that area, actually it was optimized, I believe, to work in the cell phone bands, partly because the way the resolution bandwidths are set up. And that is one of the places where these kinds of measurements are very important. When a cell tower is pretty well occupied, adjacent channel power ratio and occupied bandwidth become very important. If you don't have enough occupied bandwidth, your signal isn't getting out. If you have too much occupied bandwidth, you're spilling over into adjacent channels and you're interfering with other conversations. So that is ACPR and OCBW measurements on the Instek spectrum analyzer. Now I've set up basically the same experiment, but this time using the DSA-815 by Rigol to measure first adjacent channel power ratio, and then we'll do occupied bandwidth in just a second. Now I will point out that to do this on the Rigol, you must buy the advanced measurement function. The unit that I have came with a trial period, so I am able to do that, but if I were going to be using this on a longer term basis, my trial would expire and then I would have to buy it. And my recollection is that the advanced measurement function on the Rigol costs about $800. So it adds substantially to the price of the instrument. Remember that the Instek that I was looking at earlier, I think I only paid $900 for the whole instrument, and it includes adjacent channel power ratio as well as occupied bandwidth, so I didn't have to pay any extra. By the time you add the advanced measurement function to this Rigol, you're spending well over twice that. However, you are getting a better instrument. That is, more precise measurements, and the advanced measurements are more capable. What I have done, and I'm not going to go into too much detail, you use the measure key to set things up. You use the measure setup key to set up the various measurements. In this case, I have set up the channel spacing and so on, the same as before. And then over here you see the display, very similar to the display on the Instek. That is, at the top is the spectrum itself, and then at the bottom is a table that gives you the various values. And you'll notice that it says the adjacent channel bandwidth is 2 megahertz, the main channel bandwidth is 2, and the channel spacing is 2. And then if we go over here to the left, it tells us that the main channel power, the upper, is about minus 24, and the lower is about minus 36 or 37. Those are close to what we got with the Instek. That is, if you remember, in the Instek, the upper was worse than the lower by quite a bit. And in this case, you see the same thing. There's about a 10 or 12, maybe in some cases, a 15 dB difference between the upper channel and the lower adjacent channel power ratios. So, one thing that the Rigol gives you without you having to ask for it is the DBC. That is, instead of just giving you the upper and lower, it actually gives you the dB relative to the carrier. That's what the C stands for, is carrier. So not only do you have dBm, which are the measurements on the left, but you also have dBc, which is this column. So that's also an advantage. Now let's switch to the occupied channel. And to do that, we just, I'll back off a little so you can see what I'm doing. I'm going to press the measure again. And up here it says measurement function, and right now it's saying ACP, which is adjacent channel panel power. I'm going to go down here and instead enable occupied bandwidth. And at the top you see the spectrum again, and at the bottom you see the various values. The occupied bandwidth, it says, is about 1.93. The transmit frequency error, it also gives you, the Instek did not give you that, so that's an additional advantage. The occupied bandwidth span is once again 10 megahertz, the same as what we used, and the power ratio is in this case set to 99%. I probably should have changed that to 90% so that we could get comparable numbers. But nonetheless, the purpose of this isn't to precisely measure this particular generator, but actually to illustrate the use of these spectrum analyzers. So what I was referring to is I forgot to reset the power ratio. If you recall, on the Instek we were using 90%, and we did that not because the Instek can't do 99%, it's just that in the Instek manual the experiment is set at 90%. So that is how you do adjacent channel power ratio and occupied bandwidth on the Rigol DSA 815. Well, I think I'm going to end this part 4 on spectrum analyzers at this point. I've covered the two measurements that I wanted to cover, ACPR and OCBW, on both instruments, the Instek and the Rigol. I was planning on doing some tracking generator experiments with the Rigol. The Instek does not have a tracking generator, but I'm reminded that there are a lot of videos on YouTube about the Rigol and its tracking generator. I know Dave Jones did one or two on filters. W2AEW Allen did a couple, and I think W2CUA also did a number. So instead of that, I think what I'm just going to do is summarize what we've talked about here. The first thing that we did was reviewed a little bit on phase noise and cleared up a few areas that I may have left kind of hazy in the earlier parts. And then turning to adjacent channel power ratio and how you measure that and what it means. And finally to occupied bandwidth. So once again, I hope you've enjoyed watching this and that you've gotten a little bit out of it. If so, then maybe you'll join me for another one in the future. But for now, I'll just say thanks for watching, and see you some other time on YouTube.